cancer, stomach cancer is more common in men. It's more common in people over the age of 60. Over the last 15 years, it has now become evident that chronic infection with the bacteria H. pylori appears to cause stomach cancer. H. pylori is a bacteria that commonly causes gastritis and ulcers. Ulcers that remain untreated cause further damage to the cells in the lining of the stomach and can lead to stomach cancer. Similarly, a diet that's high in smoked foods, salted fish and meat, and pickled vegetables, foods that contain high nitrates and nitrites, are a major cause of stomach cancer. It is generally thought that the decline in incidence of stomach cancer in the United States is due to, number one, refrigeration, which means that people eat less smoked foods and salted fish and meat as ways to preserve food, as well as good treatment for H. pylori, gastritis, and ulcers. Other risk factors for stomach cancer include, again, lifestyle, obesity, and smoking, as well as having type A blood, but it is unknown why this is a risk factor for stomach cancer. How can we then prevent stomach cancer? Number one, treating H. pylori infection, eradicating chronic gastritis as well as stomach ulcers, and using refrigeration instead of salting and pickling. And our old friends, high fiber diet, avoiding smoking, and maintaining a good body weight all contribute to stomach cancer prevention. Unfortunately, there's no proven strategy for stomach cancer screening. So we still do not know how to find this cancer and eradicate it worldwide. I just wanted to take a moment to review what we've learned about the major cancers and risk factors. I think it is clear that the number one risk factor for cancers overall is smoking. It's the number one risk factor for lung cancer and is associated with a higher risk of developing virtually every other kind of cancer. In addition, we've seen in this lecture that obesity and diets that are low in fiber and high in red meat also contribute to most cancers. Furthermore, alcohol abuse is a common risk factor across many cancers. So to summarize, prevention strategies: don't smoke, don't smoke, don't smoke. And in addition, being physically active and maintaining a normal weight, as well as eating a heart-healthy diet that is low in red meat and high in fiber, are the best ways to decrease risk of developing cancer. Thank you for listening to this first lecture in the Introduction to Cancer Biology course. I hope it has given you a perspective on how cancer came to be named, what the risk factors for cancer are, where it starts in the body, and some of the screening and prevention strategies that are currently available. Future lectures will go into much more detail about the genetic cause of cancer, the different hallmarks of cancer, as well as how we diagnose cancer and how we treat it. Thank you very much. genes underlying all cancers. By the time you finish this lesson, you'll be able to describe the contribution of genes to the risk and the growth of cancer, define what a gene is, distinguish between inherited and somatic mutations. You'll be able to compare and contrast oncogenes and tumor suppressor genes, and you'll be able to describe how cancer is a genetic disease. This lesson will be delivered by Dr. Sarah Ammond. Dr. Ammond is a cancer researcher who applies ecological principles to understanding how cancer develops. She is an expert in understanding why cancer cells leave the primary tumor to metastasize to other parts of the body. As you listen to Dr. Ammond, pay special attention to the difference between oncogenes and tumor suppressor genes, and think about how they contribute to our overall goals of cancer treatment and prevention.
Welcome back to our course on an introduction to cancer biology. My name is Dr. Ammond, and today we're going to be talking about the genetics of cancer. By the end of this session, you'll be able to describe the contribution of genes to the risk and growth of cancer. You'll be able to describe what a gene is, distinguish between inherited and somatic mutation, and compare and contrast oncogenes and tumor suppressors. You'll be able to use all of this information to then describe how cancer is a genetic disease. To start off with, we'll just be going through a basic introduction to genetics. Cancer is a genetic disease, and it's caused by an accumulation of detrimental variation to the genome. It's important to remember that a single mutation is not sufficient to induce cancer formation. But before we can start to understand how cancer is a genetic disease, we need to first understand what a gene is. So a gene was first described by Gregor Mendel. He was an Austrian monk, and he's known as the father of genetics. He studied pea plants, he studied their shape, their color, and their height, and first published his findings in 1866. So this idea of genes and genetics is certainly not a new one. He described that a gene is a discrete unit of heredity of a living organism. In molecular biology, we describe gene as a region of DNA that encodes for a functional product. What we mean by a functional product is RNA or protein. Humans have about 25,000 genes in the genome, and the genome just describes all of the genes of an organism. So let's unpack this a little bit. What is DNA? DNA stands for deoxyribonucleic acid, and it's present in the nucleus of most cells of the body. DNA provides instructions for all processes of the body, and is made up of bases that bind to each other to form a twisted ladder, which is known as the double helix. What you can see in the cartoon on your left is an ideogram of what this twisted ladder looks like. Thymidine, the T, is binding to adenine, A, and the C, cytosine, is binding to guanine, G. And again, these four bases represent the bases that make up DNA. Every time a cell divides, it must replicate its DNA in order to pass on the instructions for life to its daughter cells. In a single nucleus of a cell, 5 to 6 feet of DNA are contained. So how can so much DNA be packed in such a small area without getting tangled and broken during replication? Organisms have solved this problem by packing DNA into chromosomes, which you can see in the fluorescence in situ hybridization, or FISH, that is on the right. What you see on the right are chromosomes 1 through 22 of humans, plus the sex chromosomes, in this case 2 X's. You'll notice that there are 2 for every chromosome number. This is because humans are diploid. They have 2 copies of every gene. There's 1 maternal and 1 paternal. And all of the genes of an organism contained in these chromosomes make up the genome. So then how does the information from DNA that makes up a gene become an observable trait? And that observable trait we call a phenotype. This is explained by what's known as the central dogma of molecular biology. It usually goes that DNA goes to RNA, goes to protein. So let's unpack that a little bit. Every time a cell divides, it replicates its DNA. It makes a copy of its DNA to then give to its daughter cells. This DNA stays in the nucleus, except during cell division, in order to protect it. That way we don't have more and more errors arise in the DNA over time. The RNA is the code of DNA genes, so it's transcribed or copied from the DNA. So this is then exported from the nucleus into the cytoplasm. This code, this copy of the code, the RNA, is then translated into protein. And proteins are what does the work of the cell. So proteins make up the structure of the cell. They're important for signal transduction for communication and metabolism in the cell. So then how do different types of cells do different things? Why isn't an eye cell a liver cell? Remember, every single cell in the body contains the same type of DNA. The way an eye cell and a liver cell are different are because even though every cell has the same DNA, only a subset of genes are then transcribed into RNA. And this is described in the field of epigenetics. So we can make an analogy then between genetics, genes, and epigenetics when we think about traffic patterns. The image to your left, you see cars driving on a road with traffic lights. In this case, the road describes the DNA genes. It's the same for everybody. The traffic pattern, or where the cars are actually going on the road, describes gene expression. The traffic lights regulate which cars get to drive where. It regulates which genes are transcribed into RNA in every cell. And this is known as epigenetic regulation. So this is a good time to take a break. And when we come back, we'll talk about genetic variation and mutation. So welcome back. In this section, we'll be talking about genetic variation and mutation. Let's come back to our first idea of cancer as a genetic disease. Cancer is caused by an accumulation of detrimental variation in the genome. So what is that detrimental variation in the first place, and where does it come from? It's important to remember that most genetic variation is benign, and really it's a very good thing to have in a population. The vast majority of our genomes are the same person to person, about 99.5%. That remainder, 0.5%, is variable in the human population. This variation is very small. Only one or a few bases of the DNA vary at any particular location. And those are known as polymorphisms, or single nucleotide polymorphisms, also called SNPs. The variation in our genomes accounts for our individuality. It describes why we look different from each other, why we look slightly different from our parents or children, and no one shares the exact copy of your DNA. Even your alleles may differ from each other. One variant on your maternal allele and a different variant on your paternal allele. So then, what's a mutation? A mutation is one of the few detrimental genetic variation that increases risk to developing a disease, or in rare diseases, actually causes the disease itself. When someone says that they have a cancer gene, what they actually mean is that they have a mutation in a gene that can increase cancer risk. There are two different types of so-called cancer genes, oncogenes and tumor suppressors. Oncogenes promote cancer, so in a normal healthy cell, expression of oncogenes is low, while in a cancer cell, expression of oncogenes is high. This is in contrast to tumor suppressors, which protect against cancer. So in normal cells, you'd have high expression of tumor suppressors, and in cancer cells, you would have low expression of tumor suppressors. Let's go back to our analogy of cars driving on a road. To prevent a crash, you need to both accelerate with the gas or stop with the brakes, but a balance of the two is important. This is true in normal cells. So in this case, the gas is oncogenes, and the brakes are tumor suppressors. And in cancer cells, these are both misregulated. There are two types of mutation. Activating mutation causes the gene to be expressed at the wrong time, at the wrong level, or even with a new function. So this means that activating mutations in oncogenes are tumorigenic. Their converse are inactivating mutations. And these cause reduced function of a gene, so either less RNA or protein is made. And inactivating mutations in tumor suppressors are tumorigenic. So we'll go ahead and take a break now, and when we come back, we'll talk about two-hit hypothesis and genomic instability. section, we'll be talking about two-hit hypothesis and genomic instability, and really where those mutations come from in the first place. So you can acquire mutations two different ways, either through somatic mutation or germline mutation. Somatic mutations are acquired by somatic cells, which are all the cells of the body except eggs or sperm. And those mutations are passed on to daughter cells during cell proliferation. It is important to remember that these mutations cannot be inherited by offspring. Every time a cell divides, it must replicate its DNA. And errors just get made by chance. So you'll remember what we talked about before with a lot of DNA packed into a very small area. So just by chance, about one mutation is made every 10 billion base pairs. There is an increase in DNA damage and subsequent replication error due to environmental carcinogens as well. These include UV damage, which is also shown in the cartoon to the right, where an incoming UV photon hits the DNA and damages it so that it causes nicks in the DNA, which you can see to the far right, which then have to be repaired by the cell. And this can cause an increased risk to skin cancer. Similarly, smoking causes chemical damage to lung cells, and hepatitis and alcohol abuse can lead to damaging cirrhosis of liver cells. You might remember these from another lecture where Dr. Panta discussed the risks to different cancers. The other way you can get mutations is by inheriting them, and these are called germline mutations or inherited mutations. And these mutations are present in the germ cell. So in this case, that's the egg or the sperm, and are inherited by offspring. So it's just the genetic variation that we're born with. Germline variation accounts for why offspring look similar but not identical to their parents. When cancer is said to run in families, it may be due to these inherited mutations. For example, women who inherit a BRCA1/2 mutation are at increased risk for breast cancer, and individuals who inherit a CDH1 mutation are at increased risk for stomach cancer. But not all women who inherit a BRCA1/2 mutation develop breast cancer. How does that work? This is where it becomes important to remember that cancer is caused by an accumulation of detrimental variation in the genome. The biggest risk factor for developing cancer is aging. Over time, we accumulate mutations, and this either happens by random replication error or by increased replication error due to carcinogens that cause DNA damage, as we discussed before. The two-hit hypothesis describes why not all women with a BRCA1/2 mutation get breast cancer. You'll remember that humans are diploid. We have two copies of every gene, one maternal and one paternal. This means that even if one copy of a gene or allele is mutated, the other copy can allow the protein to operate normally. In order for a gene to be cancer-inducing, both copies of the gene must be affected. The second so-called hit may alter the DNA directly via mutation, or it may alter the expression of the DNA via an epigenetic mechanism. So let's walk through an example of this. We'll walk through the top tree first. On the far left, you can see a parent who with his partner passed on two normal copies of a gene to their child. Over the lifetime of this individual, he accumulates mutations, including one hit in the gene shown here. Importantly, the other copy of the gene that was normal but did not have a mutation allowed it to be expressed normally. Eventually, however, this individual acquired another mutation in the same gene, and this resulted in the gene becoming a cancer-causing genetic mutant. In the bottom example, we see an example of inherited or germline mutation causing increased risk to an individual over a lifetime. In this case, the parents passed on one mutated copy of the gene and one normal copy of the gene. In this case, as the individual progresses through life, he only needs one additional hit in order for the gene to be cancer-causing. Most cancer requires mutations in multiple different types of genes. In order to survive, a cancer cell must overcome normal regulation of cell proliferation, cell survival, and cellular communication, and other so-called hallmarks of cancer that will be discussed by Dr. Zarif in a later lecture. Each of these processes are tightly regulated in normal cells by multiple redundant pathways. This means that in order to become cancerous, a cell must accumulate mutations in multiple of these pathways. It's been described as usually a minimum of 6 to 7 in multiple different genes. So you can see an example of this to the far right. At the top, we see a normal cell where a mutation has inactivated a tumor suppressor gene, so we see increased proliferation. This cell doesn't become malignant yet, though. First, it undergoes mutation that inactivates DNA repair genes, an additional mutation that activates an oncogene, and then mutations that inactivate several different tumor suppressor genes that then induce it to become cancer. In addition, cancer cells show a great deal of genomic instability. And genomic instability describes how cells can survive and divide with higher rates of mutation than in normal cells. So in a normal cell, DNA replication error results in programmed cell death or apoptosis, which you can see in the lighter colored box over to your right. In a cancer cell, that same DNA replication error with the same DNA replication error, cells continue to divide and pass that mutation on to daughter cells. Over time, these mutations in these repair pathways will accumulate since cells never undergo that programmed cell death, and the frequency of mutation in the cancer cell genome increases. This increase in mutation rate leads to tumor cell heterogeneity and is one of the reasons why cancer patients become resistant to treatment. This brings us to the end of our lecture. I hope this gave you a good understanding of the basics of genetics in order to better understand the rest of this lecture series, An Introduction to Cancer Biology.
I got a 70% on my quiz. But I need an 80 to pass, so I failed. But I got a 70%, which is not bad. So I'm okay. I'm okay with that. It's better than my first test was 40. So now I got a 70. Moving up.
So far, you've learned about how cancer is defined, how many people it affects, and what the common types of cancer are. You've also learned about how changes in genes underlie many of the abnormalities observed in cancer cells. Now we're going to take a look
I would
at
retake
the
it, but
hallmarks of cancer.
I'm not really
These hallmarks.
caring too much about like getting a degree or anything. I'm just kind of wanting to learn. So if I fail, I fail. But if I do want, I can go back and do it. I can surpass it for now. I can surpass that for now. I feel more grounded, Lady Ange. That's all I could say. Take care of yourself, Keller. No worries. Goodbye. That's my thoughts, Sally. That's my thoughts. Yeah. Yep. I know genetics is a tough one for me too. I would say genetics, more just like I wouldn't look into genetics too much though still. I would look more into, yes, of course, if things can be passed on, right? Things can be passed on, but I wouldn't fixate on what she's saying. Do you get what I'm saying? Like, I wouldn't fixate too much on that. I wouldn't, personally. Why? I don't know. But, I don't know. I think it's more than that. More than that. And also not always exact, but
So nice. Ouch.
Bill, please don't talk about Gregory in my chat. Thank you very much. Please and thank you. Obviously, I didn't go to Gregory, so please do not bring it up in the chat. That's my personal business. I don't need to be asking, how's Gregory? Where's Gregory? Thank you very much. Understood? I hope so. Thank you. If it's not understood, then there's a problem. Always a problem with other people. You can tell. They don't respect, they just fucking, it's a disaster.
Understand the 10 cellular hallmarks of cancer. Recognize how these cellular hallmarks distinguish a cancer cell from a normal cell. And articulate how these hallmarks make a cancer cell more fit for competing, surviving, and reproducing in the body. This lesson will be delivered by Dr. Jelani Zarif. Dr. Zarif is a cancer researcher who develops new therapies for cancer. He is particularly interested in how the body's immune system interacts with cancer cells and how this can be applied to treatment. As you listen to Dr. Zarif, pay special attention to the common properties of all cancers and the differences between oncogenes and tumor suppressor genes, and think about how they contribute to our overall goals of cancer treatment and prevention.
Dr. Jelani Zarif, and I am a prostate cancer researcher at Johns Hopkins University School of Medicine in Baltimore, Maryland. Today I'm going to talk to you about the 10 cellular hallmarks of cancer. These 10 cellular hallmarks are what distinguishes a normal eukaryotic cell from a cancerous cell. Here are some of the learning objectives of this module. First, students will be able to list and understand the 10 cellular hallmarks of cancer, understand how these cellular hallmarks distinguish a cancer cell from a normal human eukaryotic cell. Lastly, our articulate how these hallmarks make a cancer cell more fit for competing, surviving, and reproducing in its host, which is the human body. Before we go into the 10 cellular hallmarks of cancer, here are a list of terms that will be used interchangeably throughout the lecture. Apoptosis. Apoptosis is a form of programmed cellular death. Mitosis. Mitosis is a form of cellular division that results in two daughter cells. Telomere. These are sequences located at the ends of a chromosome. These have specific sequences of nucleotides, and these sequences shorten at the end of each mitotic cell cycle. Angiogenesis. Angiogenesis is the process of developing new blood vessels from pre-existing ones. And finally, metastasis. Metastasis is the process by which a cancer cell or cancer itself spreads from its origin to another part of the human body. Now that we have covered several terms, we will discuss the first 5 cellular hallmarks of cancer. We will also discuss how these cellular phenomena differ from a normal human eukaryotic cell. So before we discuss cellular hallmarks, let's revisit the eukaryotic cell. The eukaryotic cell is the smallest functional unit that can produce daughter cells in the living body. It's a word that comes from meaning small in Latin, and it is able to produce 2 daughter cells through a process called mitosis. And this process is tightly controlled. Cells are present throughout our human bodies and make up tissue, and these tissues make up organs. And so cellular homeostasis is very important in tissues and organs. The cells, as you can see from this cartoon, are made up of a number of organelles. One that's very prominent is the nucleus and the nucleolus, shown in purple, as well as the mitochondria, lysosome, the centrosome, and other organelles located in the cytoplasm. Again, the production of cells progeny is tightly controlled in a mechanism called the cell cycle. And here it is shown in a cartoon. The cell cycle is a series of events that take place in a cell leading to its division and duplication of its DNA, known as DNA replication, to produce 2 daughter cells. In the nucleus of these cells, the cell cycle is divided into 3 periods: interphase, the mitotic phase, shown by M in the cartoon, and cytokinesis, which is shown in the cartoon of the 2 daughter cells, which occurs after the mitotic phase. During the mitotic phase, again, these cells split into 2 distinct daughter cells. During the final stage, cytokinesis, the new cell is completely divided. To ensure proper division of the cell, there are several control mechanisms that occur during the cell cycle. These are known as cell cycle checkpoints. These are located in the gap phases, or the G phases, shown in the cartoon. This is germane to what distinguishes a cancer cell from that of a normal cell, and leads us to hallmark number 1. Cellular hallmark of cancer number 1 is replicative immortality. Normal human cells have a finite ability to undergo mitosis due to what is known as the end replication problem. This is largely due in part to the telomeres of the chromosomes, which are at the ends of the chromosomes. They get shorter after each mitotic division. One of the first people to observe this was Dr. Leonard Hayflick, and when cells stop dividing, they are known to have reached Hayflick's limit. And once cells reach Hayflick's limit, they can no longer divide, and they go into the G0 phase of the cell cycle, also called cellular senescence. Here in this cartoon, you can appreciate the ends of the chromosomes are pink. Those are the telomeres. And in normal cells, they can stop dividing once the telomeres become too short. However, a hallmark of cancer cells is that they are able to greatly exceed what is known as Hayflick's limit and continue to undergo mitosis. Cancer cells can greatly exceed Hayflick's limit by using an enzyme known as telomerase. Telomerase is able to elongate telomeres after they get too short to sustain proliferation. And telomerase is seen to be expressed at higher levels in several cancer types. Here's a cartoon of telomerase, and it's an enzyme that is a reverse transcriptase enzyme that adds short nucleobases shown in the cartoon as A, U, C, C to the ends of the telomeres in a 3' direction. So hallmark number 1 was replicative immortality. By cancer cells being immortal, they're able to continuously proliferate, and also they can pass on genes to daughter cells that are mutated. This leads us to hallmark number 2 of cancer, known as genome instability. In the previous lecture, Dr. Amin discussed that a gene was a unit of inheritance that consisted of 2 alleles. In this hallmark, we will see how genome instability gives rise to tumorigenesis. Hallmark number 2, genome instability. In normal eukaryotic cells, they bear 22 autosomes and 1 pair of sex chromosomes that reside in the nucleus. In a normal cell undergoing DNA synthesis during the cell cycle, if it detects a mutation, which occurs in the gap phases of the cell cycle, the cell is able to stop the cell cycle, repair the mutation, and then re-enter the cell cycle. Genes that are involved with stopping the cell cycle if a mutation is detected are known as tumor suppressor genes, which was covered in a previous lecture. So think of these genes as being the brakes in your automobiles. If you see traffic coming, you put on the brakes to stop your car or your automobile. Tumor suppressor genes work similarly. However, cancer cells differ from normal cells due to their ability to bear an abnormal amount of chromosomes within the nucleus and also still be able to undergo mitosis. Genes that are mutated in cancer or lost in cancer contribute to genome instability. These are your brakes, known as tumor suppressor genes. Conversely, there are genes that become overexpressed or mutationally activated, and these are known as oncogenes, which was covered.
Residents of the Westfield Village named Impossible Data.
So I've been off the leafy greens for the last 2 weeks, and as someone who has been an everyday leafy greener for the last 15 years, it has been a very eye-opening experience, and I'd love to talk to you all about it. I just saw a study that said for the first time in American history, there is more of a consumption of this than there is the alcohol, and I'm not gonna lie, that shocked me. I don't know how to say it, but I felt like in my personal experience, it was making me a hermit, making me super introverted, and not giving me the same sort of feelings that it used to. After I stopped playing sports in high school was when I kind of started using it a lot more. While at the beginning I felt like the greatest thing ever, something that made me laugh, something fun, something that helped me not really take my life seriously. And with my ADHD, like the only thing that really actually helped me feel like I was at baseline. But as time went on, and I don't know if you all felt this way too, I feel like it really changed like who I was as a person. I was someone who never had any anxiety, never had any stress, but over time, every time I would use it, it was giving me these extreme feelings of insecurity and lack of confidence and hardcore anxiety. I've only had maybe 5 or 6 anxiety attacks in my life, and that's 5 or 6 anxiety attacks too many. And they were all when I was way too... Anybody who says it's not addicting, like, truly doesn't know what they're talking about. I feel like fast forward to 2025, I've been in this weird conundrum of, like, I do not want to do it. Every time I was about to use, I didn't want to do it, but I felt like I had to. I knew it was going to give me anxiety. I knew it was going to lower my confidence. I knew it was going to make me feel introverted, not want to talk to anybody, but I felt like I had to. And addiction's such a weird thing, right? Like, you could be totally aware and conscious that something could be really bad for you, changes that are being made. First of all, for the first week, I was profusely sweating. Profusely sweating, especially when I was asleep, coupled with the most hardcore dreams I've ever experienced. Some really good, some horrific. Secondly, people have been commenting every single day how much different my personality has been. I'm much more talkative. I seem much happier. I have a lot more energy. And these are the things that people used to say about me in high school. And as I've kind of gotten older, I feel like I've been pretty bitter, and sometimes even to the point where I feel like I've been a little bit of a hater. And that's the absolute last thing I ever wanted. And I don't want to like completely contribute this to that stuff, the leafy greens, but I don't know. It definitely didn't help. Third, and most importantly, I'm sharper. I feel like I actually can like, retain a thought and not lose my train. You know what I'm saying? Like I can't tell you how many times I've just had a thought and somebody has talked and then that thought has just completely fleeted. And I feel bad that it's taken me this long to do this. It's kind of embarrassing that I haven't been able to have this self-control, but I can't even lie. It feels really good. And I'm curious if anybody else is going through this right now, and experiencing a weird sort of relationship with whether it's the leafy greens or alcohol or tobacco or any other substance. It's not something I've ever talked about on here, but every single video you have ever seen of me on this platform, I have been, and I don't want to be doing this shit anymore. I don't want to feel like that. I don't want to live my life like that. I don't want to feel like I have a crutch, and it's negatively affected my life in a lot of ways. And I want to hold myself accountable, and that's why I'm coming on here and talking about it. So yeah, please hold me accountable. I'm 2 weeks in. I feel great, other than, going through this breakup, but starting to feel better on all fronts. I want to use this comment section as like an open forum to talk about this, and I want this to be a safe space. No judgment, no hate over here. I haven't been making content for the last month or so, but I think I'm going to start back now. Love y'all. And yeah, starting to feel better on all fronts. I want to use this comment section as like an open forum to talk about this, and I want this to be a safe space. No judgment, no hate over here. I haven't been making content for the last month or so. 2 years ago to the day, Greece had its most fatal train accident in our country's history, and I feel like while most of the world doesn't know about this, so I've been off the leafy greens. I go to a gym in Los Angeles with some of the most entitled, douchiest people I've ever met in my life, but the craziest shit just went down in the sauna, and I have to tell you all about this. I'm not going to say the name of the gym because it's beautiful and I love going there, but anyone who knows gym culture knows that around 5, 6, 7 p.m. after the work rush, the gym is slammed. The sauna is going to be slammed. After my workout, I step into the sauna, expecting it to be packed, but today, for some reason, it was a little bit extra packed than usual. I look to my left, and there's a gentleman laying down. He's basically made a fucking bed for himself with like 6 towels. The lack of social awareness and courtesy to be doing this in a packed sauna, I think is pretty crazy. Don't get me wrong, I love laying down in the sauna, but not when there's 13 people in there, okay? Mind you, the sauna at this gym is massive. There's 2 levels. It can fit like, usually 13, 15 people actually pretty comfortably, okay? But because he is lying down, on the bottom level, by the way, which means no one can actually sit even on the top, he's taking up like 25% of the sauna by himself. Even with all that said, no one is saying anything to the guy because technically it's not a rule, okay? Should it be a rule? Yes, but technically it's not a rule, so no one's saying anything to the guy, right?
Sorry.
There's a gentleman who's sitting on the 2nd level who's kind of like next to him. He's not even that close to him, but I don't know if he had an itchy foot or something, but he just went to scratch his foot, right? And the guy who was laying down all of a sudden goes, "What the fuck, bro? What the fuck are you doing?" The audacity of the guy lying down to chirp at somebody else is mind
his foot and put it in his face and started scratching. And he's like, how you like that, bro? How you like that, bro? Beef in the sauna? Chirping someone in a 180-degree room is wild. Especially when this guy was causing all these fucking problems and no one was saying anything. So the guy who was scratching his foot is like freaked out. He's like, bro, it was an accident. Like, I'm sorry. Like, I had an itchy foot. The only reason he was even close, because, bro, you're lying down. You're lying down in the fucking sauna. He's calling him a little bitch. Fuck you, fuck you. And at this point, people are like, bro, chill out. Chill out. What are you doing? He's like, oh, fuck you guys. Fuck you guys. And he goes back. He goes back to lying down. Like nothing ever happened. And we're all like, looking at each other like, who is this fucking clown? Literally at that moment, right when he goes back to...
Jeez.
So...
Your name sounds like something Adam Sandler would say. No, Salome. I did my day at Salome.
My grandmother used to owe.
Guys, a tear just dripped down my leg.
That you can't just wait for... That you can't just wait for things to get perfect. You just go out and do stuff. And that's why it's so important. What do you do with your life, man? Why are you sitting around? Why are you waiting for shit to happen? It ain't gonna happen like that. Why are you feeling sorry for yourself? Why are you waiting for that fucking apology that's never gonna fucking come? People sit around waiting and waiting and waiting and waiting and blaming and blaming. I always tell people that about working out. Like, fuck your motivation. Fuck your motivation. You need discipline. Because motivation is not there every day. I'm missing motivation most days. Wow, some days, yeah, sometimes I got motivation. Sometimes I'm like, fuck yeah, today I felt good. I can't wait to get to the gym. A lot of days like, gotta get to the gym. And then once I get going, then I feel great. Yeah, I feel great when it's over. But it's that beginning part that's hard because your body wants to stay comfortable.
What I like about it is I'm doing something I don't want to do. Every time I start doing things I don't want to do, I grow.
Yes, that's a lesson that people need to hear.
And the angels cry. Stop your finger.
You want me to let your eye wait till y'all done?
No, that's a plan. This game is something can't make elimination.
I have a question. You want to do a reset series? This elimination is not...
No, it's the next series. It's not. He can't do it.
Does?
No, why you ignoring James?
Wait, I didn't hear. I was talking to you. I can talk to two people at one time.
Okay.
What did you want to do a reset series thing? Did you just call me weird?
I said it's weird, not you're weird. I said it's weird. You want to do a reset series with me?
When?
Tonight, you my partner.
Oh, no, I can't. I'm going to be your partner for reset.
You need respect.
Stop your finger.
There is always.
Hi, bitch. Hi, bitch. Hi, bitch. Hi, bitch. Please stop. Please stop. Please stop. Please stop. Hi, bitch.
Breaking news, Casey Anthony is now on TikTok, and after receiving tons of backlash.
Well, no, my name is Casey Anthony. My daughter is Kaylee Anthony. My parents are George and Cindy Anthony.
This message is for Casey Anthony and for Casey Anthony only. So if you're not her, keep scrolling. Yeah, listen, girl. I know you don't know who I am, but I'm just gonna give you the warning shot now. You better get off the internet before you...
For those of you who don't know, my name is Casey Anthony. As a proponent for the LGBTQ community, women's rights, I use this platform that was thrust upon me. Yes, I am on TikTok.
what you looking for. And another thing.
Okay, wait, stay tuned, guys.
Don't like that. Like this. Yeah. You're not seeing. Don't like that. Like this. Yeah. His prison is dead, hate me. I broke his little heart, he a cry, baby. If I ain't let him hit the pump by now, then that's blame if he still. Don't like that. Like this. Yeah. You're not seeing. So. DJ Khaled. Never have I ever. So maybe on somebody personal. Don't like that. Like this. Yeah. His prison.
1,000 what's up?
There. Don't like.
We are adding one of. I made this video tense. Nina to be one of our moderators. Nina, can you type a comment, bro? I made this video tense. We taking pics like that. She down my number like that. Listen to this prayer and you listen. This weekend I'm dropping a crazy. Do it. It's gonna be in the week. Do it. This weekend I'm filming a crazy YouTube. Do it.
I asked myself, how did I make it here?
But it shouldn't.
Shades on, I pull with the glass.
What up? Yeah, it's good, that course. Keeps you focused, you know? Keeps you focused. I gotta finish this one. 8 minutes left here.
In the previous lecture,
Then maybe I'll take a break.
genes cause cells to proliferate uncontrollably. You can think of these genes as your gas pedal. The gas pedal causes you to accelerate. Notable genetic alterations that occur in cancer, especially to oncogenes as well as tumor suppressor genes, are point mutations, deletions of chromosomes where tumor suppressor genes lie, as well as loss of heterozygosity and several other mutations and modifications. Here is a look at genome instability in cancer cells using a molecular biology technique called karyotyping. This is a method to assess the number of chromosomes per nuclei. If you take a look at this karyotype from CML, you will appreciate the genomic rearrangements as shown by multiple colors on chromosome 9, which is pink and white, and it's highlighted with the arrow, as well as a deletion in chromosome number 22, shown by the arrow. Normal cells will not bear such insults and continue to undergo mitosis. However, cancer cells are able to continuously divide and bear such mutations and genetic rearrangements.
I'm just gonna read this. Do you find you learn better by doing, listening, or seeing? It's listening. 100%.
So this genomic instability leads us to our third hallmark, evasion of growth suppressor signals. Mitosis in normal cells is a tightly controlled process wherein the pro and anti-proliferation signals coordinate cell
Listening is a form of communicating. So visually, you can't trust your vision too much. Listening, you can trust all you can listen to. How you feel. You remember things when you don't even think you remember it. You actually remember it. Yeah, it's nice to hear. Sometimes you don't think though. Like you get stuck because you're like, wait, what'd you say? What'd you say? But like, just let him talk. Stop like picking things out. Just chill. You'll know. Like, let it formulate. Chill. You get it.
activities at the cell cycle level. Particularly, the G1 phase of the cell cycle is a vital checkpoint wherein anti-growth signals exert their influence to block cellular
Not
proliferation.
process without listening. You have to listen, but you don't have to get stuck. You don't have to get fixated. Because that's the problem with listening. Just you wait till it's all done and then move forward. It might even hit your brain a couple hours later. Maybe a couple hours later it'll hit your brain. Sometimes it takes a while. And then you're like, oh fuck, that makes sense to why he said it like that.
However, due to hallmark number 2, genomic instability, most cancer cells are able to circumvent normal growth suppressor signals
Yeah,
at the
like-
G1 checkpoint.
When I'm listening, I'm just taking it in and then doing the test with my best ability. That's what you're supposed to do. You're not supposed to second guess yourself. You're supposed to listen, let the video change, give it your all with your first, you know? So, it works. You have to trust your first instinct instead of soaking yourself, you know? For me,
In order to
whatever.
continue to proliferate. Again, how cancer cells are able to evade growth suppressor signals. One mechanism is a tumor suppressor gene called retinoblastoma, or RB. RB actively inhibits cell passage through the restriction point in the G1 cell cycle phase. Cancer cells with mutated RB remove this gatekeeper for ongoing cellular proliferation. Another tumor suppressor gene called P53 is lost in many cancer types. This allows for the cell cycle to progress despite DNA damage and other cellular stresses that will kill a normal cell. With these gatekeeper genes lost or mutated, cancer cells are able to sustain proliferation and resist cellular death, which is hallmark number 4. Hallmark number 4, resistance to cell death. Normal cells can initiate cell death, also known as
The problem for me, oh my god, sorry. I lose my train of thought when I hear fucking things downstairs being fucking. People need to take their time with things. Put a fork down nicely. Take some care when you do things. I don't need to hear a bunch of distractions. Anyway, I lost what I was saying, but I would listen and read over and over. The only problem with that is you're like stalling. Trying to figure it out when it could figure out down the road. I would suggest just getting the information in, moving on to the next information. That's the best way to do. I don't get easily distracted, no. That's not the case. I take in what I want to take in. So if I hear somebody not really taking their time or caring, it bugs me because that's not what I want for myself. So yes, I might be picky, but I don't blame myself saying I get distracted easily, Kathy. No. Sorry. Not saying you are, but just showing the world what it really is, to be honest with you. Thank you.
Mitosis in response to an abundance of DNA damage, DNA mutations, as well as other cellular stresses from external
It's called
factors.
respect.
As I stated in the previous slide,
Some people don't know it.
a cancer cell can continue to cycle through the cell cycle while bearing such DNA damage and other cellular stresses. Cancer cells are also able to resist cell death by upregulating pro-survival proteins to avoid cell death in the presence of these stresses. One example of a pro-survival protein that's seen overexpressed in many cancer types is the pro-survival protein BCL2. BCL2 has anti-apoptotic family members such as BCL2, BCLXL, MCL1, SID9, A1, BFL1, and also pro-apoptotic family members such as BAX, BAC, BCLXS, BIM, and a host of others. Here's a cartoon illustrating that. In many cancer types, we see BCLXL and BCL2 family members particularly overexpressed.
I believe taking notes is a waste of time. I really do. I think if you want to understand something, you should just understand it. Instead of thinking, how am I going to build this into me? Just build it into you and trust your instincts. Truly, for me, experienced.
And as shown here in the method used in molecular biology called immunohistochemistry. This is BCL
Going back and
that
listening
is
if you missed it.
overexpressed in lymphoma, and you can appreciate the brown are BCL-XL positive cells in this immunohistochemistry slide. Because cancer cells are able to
For me,
resist
that's
cell
what I
death,
said,
they are
sorry.
able to
So.
sustain proliferation. With all the previous hallmarks, they're able to do this quite easily. Within normal cells, growth factor signaling is also tightly controlled for tissue homeostasis and other cellular functions. Cancer cells are very different, and they have the ability to proliferate, as I mentioned in hallmarks 1 through 4, with loss of tumor suppressor genes, as well as overexpression of oncogenes, such as RAS, SARC, and many others. Cancer cells also have the ability to stimulate the
If you like taking notes, you should tell us why. We don't really care what you like. We're kind of here to learn.
normal cells that
Just like I
surround
do.
them in what is known as the tumor microenvironment to provide them with essential growth factors.
Just common sense.
One growth factor that's well studied in cancer research is called the epidermal growth factor.
It's
Epidermal
just
growth
common
factor
sense.
can bind to the receptor which is expressed on cancer cells known as EGFR to
People learn
activate
differently, people learn less, and people learn more. That's how I look at it. So yeah, people do learn different.
an oncogene well studied in cancer research called RAS. And RAS can have downstream effects that positively regulate cell proliferation of cancer cells.
You don't have to go like that.
So here's a quick review over hallmarks 3
Cool.
through 5. So a normal cell compared to a cancer cell. So a normal cell, when it detects DNA damage, P53, a tumor suppressor gene, stops the cell from cycling.
Well, memory is practiced. Right? Why do you do that? Another biased mention. Just very absurd, to be honest. Why? Why? Just so you can write in my journal? Why? Why? Ask yourself that. Find out an answer.
Cell into cellular arrest, repairs the DNA, and the cell is able to go back into the cell cycle. That's one option. If there is too much DNA damage, the cell is signaled to go into apoptosis, and then the dead cell is then cleared by phagocytes, and this leads to cellular and genetic and tissue homeostasis.
Just because you're DNA, though, doesn't mean you go through the same experiences. You know, experience also means a lot. So that's why I wouldn't be so fixated on DNA. Because how you live is mostly why you're affected with things. That's my opinion.
However,
I wouldn't focus too much on like DNA. I'd focus more on, because DNA can also be manipulated nowadays. DNA can be changed. DNA can be tangled. It can be all of that. So I wouldn't focus too much on that. That's what I was trying to say before. But I get where you're going with it. I do. I understand, but I don't agree with it.
There's a loss or mutation of P53 where it does not function correctly.
I understand,
the cell
though.
has aberrant mutations.
It's not like I
The
don't
cell
agree
is not
totally,
able to
just like
leave the cell
overall.
cycle, and instead it continues to proliferate and go through the cell cycle unchecked. It does not undergo apoptosis, and you.
Environment can play a big role. Yeah, I think environment, like if what you're doing to yourself, right? Like if there's poison that we don't use, we shouldn't be smoking, right? Because then it's poison. And then also like intake, like what we're eating, but I look at that as environment. Like what you eat, intake, all that's like environment, you know? But all of those things can be worked on. So that's a good thing. Even your DNA can be, like, it's changed. It's affected, which means if something's affected, that means it's not the same as it was before, right? It's cool that a child will always be a part of the mother. Not really to me, to be honest with you. To be honest, I don't really get fantasized. I don't really think that's that interesting, to be honest. It doesn't fascinate me. So, sorry, but it doesn't. Yeah, it doesn't.
So here are the first 5 hallmarks that we have covered in this lecture. Hallmark number 1, replicative immortality. Hallmark number 2, genome instability.
I don't know.
Hallmark number 3,
Just doesn't.
evading growth suppression.
It does for you, apparently, and that's okay. Good for you.
Sustained proliferation.
That's awesome.
Hallmark number 5,
But
resists
for me, it doesn't.
cellular death. So that is it for this section. I think you can appreciate the first 5 cellular hallmarks of cancer. You will now
Sure.
have a short quiz, and in the next session, we'll discuss the next
Yeah,
set of
exactly.
cellular
I
hallmarks of
agree.
cancer.
I'm not sorry. Never said I was sorry. If I did, it was just. I'm not sorry. Just telling you. Just telling you. Definitely not sorry. Perfect. No, I'm not interested in that as well. Stephanie, no. Not yet. Maybe one day I will, but I'm not. It's going good, Jersey girl. It's going good. That one's hard, man. I don't know. Oh man, maybe all. Fuck. Okay. I'm failing this test for sure, guys. Jeez. This is not good. Oh yeah. Fuck. I don't know, man. I think, yeah, I would say that. Oh my god, that's horrible. I got every question wrong. Whatever. It is what it is. We'll go back.
Our next session, we will discuss emerging hallmarks of cancer.
Most of the questions was like, is it RB or P53, whatever, and then I would say, oh, P53, I've heard that, and then it'd be like, no, it's both. So it'd be like, I'd miss like saying it's all of it or none of the above, because I would think like, oh, it's definitely that one, instead of just like picking, you know. So that's why I fucked that one. I kept picking the wrong one. I kept picking the wrong one. Yeah, man, those are tricky. Alrighty, guys, I'm gonna take a little break. I'm pretty sure just for a little bit, but I'll be on in a little bit. But I'm gonna take a little break. I'm gonna answer some cameos for a bit, but I'll see you guys later. Okay? Okay, bye, guys.